State, with reasons, a different material suitable for each of the following applications. A. A large motor vessel propeller. Material, typically made of a bronze alloy, such as NiAl, nickel aluminium bronze, or aluminium bronze. These alloys are chosen for their strength, toughness, and resistance to corrosion in seawater. B. A centrifugal pump impeller. Material, often made of stainless steel for its strength, corrosion resistance, and ability to handle abrasive fluids. In some cases, cast iron or nickel aluminium bronze may be used depending on the specific application and cost considerations. C. A seawater cooled heat exchanger tube. Material, typically made of titanium or cupronickel. Titanium offers excellent corrosion resistance and strength, but is more expensive. Cupronickel is a more cost-effective option with good corrosion resistance and heat transfer properties. D. A 300 mm diameter seawater cooling pipe. Material, often made of fiberglass reinforced plastic, FRP, which is lightweight, corrosion resistant, and relatively inexpensive. In some cases, steel or high-density polyethylene, HDPE, may be used depending on the specific requirements and pressure rating. E. A cylinder head of a small auxiliary engine. Material, typically made of cast iron due to its good machinability, heat transfer properties, and affordability. In some high-performance engines, aluminium or aluminium alloys may be used for their weight-saving benefits. With reference to aluminium, A. Explain what is meant by work hardening. B. Describe the internal changes when it becomes work hardened. C. State the effect work hardening has on its properties. D. Describe how it could be annealed on board a vessel. A. Work hardening explained. Work hardening, also known as strain hardening, is a phenomenon where the strength and hardness of aluminium increase as it is plastically deformed, i.e. bent or stretched or hammered. This doesn't involve any change in its chemical composition, but rather a rearrangement of its internal structure. If you think of aluminium as a pile of spaghetti strands in its soft state, the strands are loosely tangled, but when deformed, the strands get much more tangled and interlocked, making it harder to further deform them. This increased resistance to deformation translates to a higher strength and hardness. B. Internal changes during work hardening. During work hardening, several internal changes occur within the aluminium. Dislocation formation. Plastic deformation creates defects called dislocations in the crystal lattice of aluminium. These dislocations act as obstacles to further movement of atoms, hindering deformation and thus increasing strength. Grain refinement. In some cases, severe deformation can break down larger aluminium grains into smaller ones. This also contributes to work hardening because smaller grains have more grain boundaries, which again act as obstacles to deformation. C. Effects of work hardening on properties. Work hardening has both positive and negative effects on aluminium. On the positive side, there is increased strength and hardness. As explained above, work hardening makes aluminium stronger and harder, making it suitable for applications requiring higher load-bearing capacity. There's improved wear resistance. The increased hardness also enhances the material's resistance to wear and tear. Negatively, you have reduced ductility and malleability. The tangled grain structure makes the metal less ductile, stretchable, and malleable, formable. This can limit its usability in applications requiring bending or shaping. Increased brittleness. Severe work hardening can also make aluminium brittle, making it more prone to cracking and failure under high stress. D. Annealing aluminium on a vessel. Annealing is a process that reverses the effects of work hardening, restoring the aluminium to its original soft and workable state. On a vessel, this can be achieved through either flame annealing, where a handheld torch is used to locally heat the work-hardened area above a specific temperature, around 350 Celsius. This softens the crystal structure and relieves internal stresses, restoring ductility and malleability. There's also induction annealing, where a portable induction heating coil is used to generate heat within the metal. This method offers precise control over the heating process and is suitable for areas with limited access. These methods are chosen based on the specific application and size of the work-hardened part. Regardless of the method, it's essential to control the annealing temperature and duration to achieve the desired result without melting or weakening weakening the aluminium. List 4 methods for non-destructive crack detection. Describe 2 procedures from the methods listed above. 4 methods. 1. Visual inspection. While seemingly simple, trained inspectors can often identify surface cracks and other defects under proper lighting and magnification. This method is quick and accessible but limited to surface floors. 2. Dye penetrate testing, PT. A colored liquid is applied to the surface and allowed to seep into cracks. After wiping the surface, a developer draws the dye back out, highlighting crack locations. This is effective for surface and near surface cracks but requires careful cleaning and interpretation. 3. Ultrasonic testing, UT. High frequency sound waves are transmitted through the material and reflected back. Cracks disrupt the wave path, generating signals detected by the receiver, indicating their presence and location. This works for internal and surface cracks but requires skilled operators and specialized equipment. Eddy current testing, ET. Magnetic fields induced by a coil interact with the material and cracks affect the resulting electrical currents. This method works best for surface and near surface cracks in conductive materials like metals and can be automated for rapid inspection. B. 2 procedure descriptions. 1. Ultrasonic testing. The process. A transducer sends short bursts of ultrasound waves into the material at specific angles. These waves propagate and reflect back from interfaces within the material, including cracks. The received signals are analyzed to determine the time and intensity of reflections, its strengths. It can detect internal and surface cracks, pinpoint crack location and depth, and evaluate crack severity. It works on various materials, including metals, composites, and ceramics. Its limitations: it requires skilled operators and specialized equipment. Interpretation of signals can be complex, and access to both sides of the material may be needed. 2. Eddy current testing, ET. The process. A coil generates an alternating magnetic field that induces eddy currents in the material. Cracks disrupt the flow of these currents, causing changes in the electromagnetic field, which is detected by the coil. These changes are analyzed to identify crack locations and characteristics. Its strengths: it's fast and can be automated, suitable for surface and near surface crack detection in conductive materials. It can be used for continuous monitoring during fabrication and manufacturing operations. Limitations: it only works on conductive materials. It's less effective on deep cracks and requires careful calibration and interpretation of readings. These are just 2 examples, and the choice of method depends on the specific material, crack type, application, and desired level of detail. Describe, with the aid of sketches, 5 defects that may be present on a weld produced using the covered electrode welding process. Covered electrode welding is a versatile and widely used process, but even the most skilled welder can encounter imperfections. Here are 5 common defects you might find on a weld, along with simple sketches to visualize them. 1. Slag inclusion. From the sketch, imagine a dark, irregular line embedded within the weld bead. Description: small pieces of molten slag, residue from the electrode coating, become trapped within the weld metal as it solidifies. Causes: improper cleaning of the joint, incorrect welding angle, excessive current. Effects: weakened weld strength, potential cracking, and there is a corrosion risk. 2. Undercut. From the sketch, picture a groove at the toe of the weld where the base metal dips below the level of the weld bead. Description: excessive melting of the base metal at the edge of the weld, creating a groove or undercut. Causes: high welding current, excessive travel speed, incorrect electrode angle. Effects: reduced weld cross-sectional area, weakened joint, increased stress concentration. 3. Porosity. From the sketch, imagine small round voids or gas pockets scattered throughout the weld bead. Description: gas bubbles entrapped within the molten metal during solidification. Causes: moisture on the base metal or electrode, improper shielding gas flow, contamination. Effects: weakened weld strength, potential leakage paths, reduced fatigue life. 4. Incomplete fusion. From the sketch, picture a gap or lack of bonding between the weld metal and the base metal. Description: the weld metal doesn't fully penetrate and bond with the base metal, leaving unfilled areas. Causes: low welding current, improper electrode manipulation, inadequate joint preparation. Effects: weak joint, potential cracking, structural failure risk. 5. Spatter. From the sketch, imagine small, solidified droplets of metal scattered around the weld area. Description: molten metal droplets ejected from the arc during welding, sticking to the surrounding surface. Causes: incorrect electrode angle, excessive current, worn-out electrode. Effects: aesthetically undesirable, potential surface damage, cleaning challenges. With reference to the cathodic protection of hull fittings. A. Explain how sacrificial anodes achieve this. B. State where sacrificial anodes would be fitted and why. C. Describe an impressed current system, stating the principle on which it works. A. Sacrificial anodes, guardians of the hull. Imagine these gallant knights made of zinc or aluminium standing guard on the hull, sacrificing themselves to protect the nobler metals around them. These are sacrificial anodes, the champions of cathodic protection for hull fittings. They work by creating a galvanic cell with the steel hull. 1. Potential difference. Sacrificial anodes have a lower electrochemical potential than the steel hull. This creates a voltage difference between them. 2. Anode and cathode formation. The sacrificial anode releases electrons and dissolves into ions. The steel hull becomes the cathode, attracting electrons. 3. Electron flow. Electrons flow from the anode through the conductive seawater to the cathode, the hull. 4. Cathodic reaction. Electrons at the cathode react with oxygen and water to form harmless compounds like hydroxide ions. This cycle essentially shifts the corrosion away from the hull onto the sacrificial anode. As the anode corrodes, it gradually shrinks, eventually needing replacement. But during its sacrifice, it protects the hull from the ravages of corrosion. B. Strategic positioning. Sacrificial anodes are strategically positioned on the hull, focusing on areas most susceptible to corrosion. Propeller. The spinning propeller creates turbulence, accelerating corrosion. Anodes near the propeller ensure its protection. Rudder and stem. These areas experience high water flow and stress, making them vulnerable. Strategically placed anodes shield them. Seawater inlets and outlets. Where water enters and exits the hull, corrosion risk is high. Anodes protect these crucial points. Bilge keels. These protrusions on the hull bottom are prone to corrosion, and anodes strategically placed underneath offer protection. By placing anodes in these vulnerable areas, we ensure that the vital parts of the hull remain shielded from corrosion, extending their lifespan and safeguarding the vehicle's integrity. For situations where sacrificial anodes aren't sufficient, or for more precise control an impressed circuit system can be employed. This system operates based on the same principle of cathodic protection, but uses an external power source. 1. Reference electrode. A reference electrode measures the hull potential against seawater. 2. Control unit. The control unit analyzes the potential and adjusts the current output from a DC power source. 3. Anode. A specially designed anode, often made of platinum or graphite, releases current into the seawater. 4. Electron flow. The current flows from the anode through the seawater to the hull, making it the cathode. 5. Cathodic reaction. Similar to sacrificial anodes, electrons on the hull react with oxygen and water to form harmless compounds. By adjusting the current output, the system can precisely control the cathodic protection over the entire hull surface. This offers advantages like tailored protection. Adjusting the current allows for customized protection for different hull areas and materials. Longer anode life. Impressed current systems can use non-sacrificial anodes which last much longer than sacrificial ones. Remote monitoring. The systems can be monitored and controlled remotely, simplifying maintenance and adjustments. However, impressed current systems are more complex and require additional maintenance compared to sacrificial anodes. Choosing the right approach depends on the size and complexity of the vessel, specific corrosion risks, and operational requirements. Remember, both sacrificial anodes and impressed current systems play crucial roles in protecting hull fittings from corrosion, ensuring the safety and longevity of vessels. With reference to osmosis in glass reinforced plastic GRP hulls, A. Explain how osmosis may be detected in service. B. Explain why simply drying out the hull is not a cure for the effects of osmosis. C. Describe the full process for the treatment of a hull suffering from the effects of osmosis. A. How osmosis may be detected in service. Osmosis is a process where water diffuses through a semi-permeable membrane from a less concentrated solution to a more concentrated one. In the case of GRP hulls, the semi-permeable membrane is the gel coat, and the more concentrated solution is the seawater outside the hull. This can cause the gel coat to blister and delaminate. Ways to detect osmosis in service. 1. Visual inspection. Look for blisters, cracks, or changes in the colour or texture of the gel coat. 2. Tapping. Gently tap on the hull with a mallet or other blunt object. A hollow sound may indicate delamination beneath the surface. 3. Moisture meter. Use a moisture meter to measure the moisture content of the hull. This can be a more quantitative way to detect osmosis. B. Why simply drying out the hull is not a cure for the effects of osmosis. Simply drying out the hull will not cure the effects of osmosis because it does not address the underlying cause of the problem, which is the presence of water trapped within the laminate. Once water has entered the laminate, it can react with the resin and cause it to break down. Even if the hull is dried out, the damage has already been done, and the blisters and delamination will likely reappear. C. Full process for the treatment of a hull suffering from the effects of osmosis. The full process for treating a hull suffering from osmosis is a complex one and can vary depending on the severity of the damage. However, here are the general steps involved. 1. Cleaning and drying the hull. The hull must be thoroughly cleaned to remove any dirt, grime or salt deposits. It should then be dried out completely, ideally using a combination of heat and ventilation. 2. Grinding. The blisters and any delaminated areas must be ground out to remove the damaged material. 3. Neutralizing the acids. The exposed laminate must be neutralized to remove any acidic salts that can cause further damage. 4. Filling and fairing. The ground out areas must be filled with a suitable epoxy filler and faired smooth. 5. Relaminating. A new layer of gel coat or epoxy resin must be applied to the repaired areas. 6. Painting. The hull may need to be repainted to restore its appearance and protect it from further damage. Describe, with the aid of a sketch, a flotation device that produces an output signal to remotely control the liquid level in a tank. Here's an example of a flotation device that produces an output signal for remotely controlling the liquid level in a tank along with the sketch. We look at the sketch. 1. Tank depicts the storage tank containing the liquid being monitored. 2. Float. A hollow, buoyant cylinder, shown in red, floats atop the liquid surface. 3. Guide rod. A vertical rod attached to the tank's top guides the float movement vertically. Magnet. A permanent magnet is mounted inside the float, facing downwards. 5. Reed switch. One or more reed switches, magnetically sensitive switches, are positioned along the guide rod at predetermined levels within the tank. Wiring. Each reed switch connects to a dedicated wire running to the control unit. Operation. As the liquid level rises, the float moves up along the guide rod. The magnet inside the float triggers the reed switch positioned at the corresponding level as it passes by. The activated reed switch completes the circuit for its associated wire, sending an electrical signal to the control unit. The control unit interprets the signal based on which the reed switch was activated, indicating the liquid level reaching that specific point. Depending on the system configuration, the control unit can then activate pumps, valves, or other devices to maintain the desired liquid level in the tank. Benefits. It's non-invasive, no contact with the liquid, minimizing contamination or maintenance needs. Reliable, simple and robust design with minimal moving parts. Customizable. Multiple reed switches can be used to create multi-level control. Limitations. Accuracy. Limited to discrete level readings at the position of the reed switches. Sensitivity. May not be suitable for highly precise level control requirements. Choosing the right type of flotation device depends on factors like desired level control precision, system complexity, and cost considerations. Fail safe, fail set, and control valves. A. Explain the term fail safe in a control system, stating 2 examples where this term is applied. B. Explain the term fail set in a control system, stating 2 examples where this term is applied. C. State what is meant by a 4 to 3 control valve. A. Failsafe. Explanation. In a control system, a fail-safe mechanism ensures that the system transitions to a safe state whenever a component failure or unexpected event occurs. It prioritizes safety over normal operation, preventing potential harm or damage. Examples. 1. Emergency brakes. In a train control system, the brakes automatically engage if the driver loses control or a sensor detects excessive speed, ensuring passenger safety regardless of human error or equipment malfunction. 2. Pressure release valves. In a chemical reactor, a pressure relief valve automatically opens if pressure builds beyond a safe limit, preventing explosions or container ruptures. B. Fail set. Explanation. Unlike fail safe, fail set prioritizes maintaining the system's current or predetermined state even if a component fails. This can be advantageous in situations where a sudden shift to a safe state could be detrimental. Examples. 1. Aircraft autopilot. The autopilot may hold the current flight path and altitude even if a sensor malfunctions, allowing time for crew intervention and safe manual control. 2. Nuclear reactor control rods. Fail-set mechanisms may ensure control rods remain inserted in the reactor core in case of sensor or actuator failure, preventing an uncontrolled chain reaction. C. 4 to 3 control valves. Explanation. This refers to a specific type of control valve characterized by a flow characteristic where a 40% opening of the valve allows 30% of the total flow to pass through. This means that the valve has a progressive flow response, slowly increasing flow with increasing opening. Applications. Precise flow control. In situations where fine adjustments are crucial, like chemical dosing or temperature regulation, a 4 to 3 valve provides better control over small flow changes compared to linear valves. Anti-cavitation. The gradual flow increase reduces fluid pressure changes near the valve seat, minimizing cavitation and noise generation, making it suitable for high-pressure applications. For the automatic closed-loop engine cooling control system shown in the figure, A. Identify the signal paths A, B, and C. B. Describe the function of the comparator. C. Name and describe the function of component D. And D. State a suitable device capable of producing a varying signal at T. A. Signal paths. Path A. This path carries the coolant temperature signal from the temperature sensor to the comparator. Path B. This path carries the control signal from the comparator to the cooler fan. Path C. This path carries the control signal from the temperature sensor via the controller to the electrically controlled 3-way valve. B. Comparator function. The comparator compares the coolant temperature signal, path A, with a reference voltage, set point temperature. If the coolant temperature is higher than the set point, the comparator puts out a high signal to path B. This high signal activates the cooler fan to start cooling the engine. When the coolant temperature reaches the set point, the comparator outputs a low signal, turning off the cooler fan. C. Component D and its function. Component D is an electrically controlled three-way valve. It provides variable flow control. D. Device at T for varying signal. A suitable device capable of producing a varying signal at T would be a temperature sensor. This sensor would convert the engine oil temperature into an electrical signal. This signal could then be used to adjust the set point temperature of the comparator based on the engine's operating conditions. This would allow for more dynamic and efficient cooling control.